Hello everyone, my name's Dr. Vile and welcome to my A-Level Chemistry YouTube channel. The purpose of this channel is all about getting you ready for your A-Level Chemistry exams, and this video is going to focus on topic 4.4, which is all about aldehydes and ketones. So it's an A2 section of the work on organic chemistry, and we're going to go through all the things that you need to know for this topic. If you find the videos helpful, remember to like, subscribe, share with your friends, keep checking back because I'm updating it regularly with more content. Okay, so this first section is going to focus on the functional group of an aldehyde. Now, an aldehyde group has a carbon double bond to oxygen, a single bond to hydrogen, and then a bond to the rest of the molecule. So it's a carbon double bond to oxygen at the end of the chain. And there are several reactions of aldehydes that we need to be aware of. They can be oxidized to give the carboxylic acid. And they can be reduced to give a primary alcohol. So we've got these two different things that are happening here. Whilst we're on this, it's worth noting as well that you can go straight from a carboxylic acid to a primary alcohol. We'll add this arrow here. And you can also go straight from an alcohol to a carboxylic acid, which is this arrow here. And we need to know the reagents and conditions to cover all of these arrows. So I'm going to label them. I'm going to label this arrow 1. Which is to go from an aldehyde to a carboxylic acid. I'm also going to label this arrow here to go from a primary alcohol to a carboxylic acid, arrow number 1, because it's the same conditions. I'm going to label this arrow 2, so that's to go from the aldehyde to the alcohol, and I'll label this arrow 3. And I'll just very quickly go through what you need in terms of reagents and conditions for each of these arrows. So arrow 1 is the full oxidation. So it's either the oxidation of the aldehyde straight to the carboxylic acid or of the primary alcohol. And for arrow 1, you need excess H+ and potassium dichromate. So excess H+ / K2 Cr2 O7. And you need to reflux. So that's arrow 1. I also want to add another arrow here that I missed off the first time, going from the primary alcohol through to the aldehyde, and let's call that arrow 4. Okay, so arrow 1, you reflux either your aldehyde or your primary alcohol with excess acidified potassium dichromate, and that'll fully oxidize it. So arrow 2 enables you to go from the aldehyde and reduce it down to the primary alcohol, and the reagent that you need is sodium borohydride, NaBH4, which is a weak reducing agent and it's capable of reducing the aldehyde. However, notice arrow 3 is also a reduction to go from the carboxylic acid to the alcohol. Sodium borohydride isn't powerful enough for that reaction, so we need something else. So for arrow 3, you need lithium aluminium hydride, which is a more powerful reducing agent. And that needs to be under anhydrous conditions, so no water whatsoever. And the solvent is epoxyethane, which is a nice dry solvent once it's been distilled. So epoxyethane for arrow 3, there is the solvent. It's worth noting that the lithium aluminium hydride used in arrow 3 will also work in arrow 2. So if you're struggling on the exam to think of what it is, arrow 2, their aldehyde to a primary alcohol, you could also use lithium aluminium hydride. And then our last arrow is arrow 4. And arrow 4 takes you from the primary alcohol to the aldehyde. This is partial oxidation. And to do partial oxidation, you need excess of the alcohol this time, as opposed to excess of the oxidizing agent. So excess alcohol. You still need your H+ and the potassium dichromate, K2Cr2O7. But this time you distill the aldehyde as soon as it forms to stop it oxidizing further. So you distill the aldehyde as it forms. So you need to be aware of all your reagents and conditions for those transformations. The same chemistry applies to ketones. So let's just draw out a ketone a second. You have a carbon double bond to oxygen, but this time it's in the middle of a chain, not at the end of the chain. So here's your ketone, and we need to be able to convert between a ketone and a secondary alcohol. So a secondary alcohol would look pretty similar, but you'd have an OH group rather than the C double bond O, and therefore this must be a hydrogen here. And you're going to be able to convert from the alcohol to the ketone, and from the ketone back to the alcohol. So we'll call this arrow number 1, and this arrow number 2. So for arrow 1, you are oxidizing the secondary alcohol to the ketone. You use the same conditions as for the full oxidation we just saw. So that is excess H plus and potassium dichromate K2Cr2O7, and you reflux that. And that's your full oxidation. And the reverse of the full oxidation is the reduction. And to reduce a ketone to a secondary alcohol, we just use the sodium borohydride we just talked about. However, it's worth noting that the lithium aluminium hydride will work as well for that reaction. But if you say lithium aluminium hydride, remember you need to talk about anhydrous conditions. In practice, you'd use the sodium borohydride because lithium aluminium hydride is more expensive. It's a bit more unsafe to work with, so it's better to use the sodium borohydride if you can. We now need to be able to distinguish between aldehydes and ketones using a chemical test. There are two possibilities that you could talk about here. You could talk about using Tollen's reagent, or the alternative is something called Fehling's reagent. Now, Tollen's reagent, we don't need to know any more details in the WJEC spec about what it is. However, just for, I think it's really helpful to know that the Tollen's reagent contains the silver 1+ ion. And the silver 1+ ion gets reduced to form metallic silver, and therefore it can oxidize something else. So the Tollen's reagent ends up giving a silver mirror for aldehydes. And no reaction for the ketone. So Tollen's reagent has this silver 1+ ion which gets reduced to form metallic silver, which is what you see. And this will give a result for aldehydes, and the reason is aldehydes can be oxidized to the carboxylic acids, whereas ketones can't be oxidized any further. The alternative is to use Fehling's reagent. Now, Fehling's reagent contains the copper 2+ ion, which gets reduced to copper 1+, and therefore it can oxidize the aldehyde and not the ketone. And what you get is a red-brown precipitate for aldehydes, but not for ketones. So if you're asked to distinguish between aldehydes and ketones, use either Tollen's or Fehling's reagent. Tollen's will give you the silver mirror for an aldehyde, not for the ketone, whereas Fehling's reagent will give you this red-brown precipitate for aldehydes and nothing for the ketones. Okay, next up we're going to look at one of the characteristic reactions of both aldehydes and ketones, and that is that they will undergo nucleophilic addition. And the reaction that illustrates this is the reaction between either the aldehyde or the ketone and hydrogen cyanide. So here we've got a ketone, R to C double bond O to R. If you react it with HCN, the hydrogen bonds to the oxygen to form an alcohol, and then this CN, which is the nitrile or the cyanide ion, attacks this carbon, forming a new carbon-to-carbon bond. So you end up forming a hydroxynitrile as the product, and we need to understand the mechanism of this reaction. So I'm going to draw that out for you and talk you through it. So firstly, for the mechanism, draw out your ketone. I'm just going to focus on ketones for a second, and notice that this carbon to oxygen double bond is polar. So the carbon is delta positive and the oxygen is delta negative. And then along comes the cyanide ion from the hydrogen cyanide, so that's C triple bond N, but the carbon has a negative charge on it. And what happens is the negatively charged carbon is attracted to the delta positive carbon, forming a new carbon-to-carbon bond. And then this carbon double bond to oxygen breaks, so we push the curly arrows onto the oxygen. And then in terms of the intermediate that forms, you've got this R to C to R still, and that hasn't changed. The double bond to oxygen has now become a single bond, and the oxygen is now negatively charged because it's gained electrons from the double bond. And we formed a new carbon-to-carbon bond, and then we have our carbon to nitrogen triple bond. And remember that hydrogen cyanide consists of hydrogen and cyanide, so there's some H plus ions in solution here, and your O minus is attracted to the H plus, and that takes you through to our product, which is the hydroxynitrile. Okay, so in this section, what we're going to do is focus on the nucleophilic addition mechanism, but for an aldehyde instead of a ketone. The good news is it's exactly the same. So you take your aldehyde, I've just gone R to C double bond O to H. So remember, an aldehyde is at the end of a chain. React it with hydrogen cyanide, and we form the hydroxynitrile at the end of the chain. So in terms of the mechanism, as I say, it's exactly the same as on the previous slide. So if you understood that, this should be just a little bit of revision for you. You draw out your aldehyde. You show the polarity of the carbon to oxygen double bond. So delta minus on the oxygen and delta plus on the carbon. Make that a bit clearer for you. And then along comes the cyanide ion, C triple bond N, with a minus charge on the carbon. And the negatively charged carbon is attracted to the delta positive carbon here. So we have a curly arrow going from the negative charge to the carbon. And then this double bond breaks, so the electrons move from the middle of the double bond onto the oxygen. And then we draw out the intermediate, so that's R to C to H. Now the double bond is now a single bond to oxygen, and the oxygen has now gained a negative charge. And then we have a new carbon-to-carbon bond and your carbon to nitrogen triple bond. And then remember, it's hydrogen cyanide, so we've got some hydrogen ions in solution, H plus. And what happens is the O minus is attracted to the H plus, we form a new oxygen to hydrogen bond, and therefore our product comes out as R to C to OH to H to C triple bond N. So we formed our hydroxynitrile, and it's nucleophilic addition. The cyanide is acting as a nucleophile. A nucleophile is something that is negatively charged, so it's electron rich, has an extra pair of electrons, and is attracted to something that is positive. And it's addition because we are adding the hydrogen cyanide across the double bond. So if I add a bit of colour to this, I can show you what I mean by that. Here's the hydrogen in yellow, and it ends up here. And here's the carbon and the nitrogen from the cyanide, and that ends up here. So it's nucleophilic addition. Next reaction on the specification for this unit is the reaction of an aldehyde and a ketone, sometimes referred to as a carbonyl group, with a reagent called 2,4-dinitrophenyl phenylhydrazine. It just rolls off the tongue, doesn't it? Sometimes this is referred to or shortened to 2, oh, don't want to write in yellow, 2,4-DNPH, a little bit easier to remember. And basically 2,4-dinitrophenylhydrazine is this molecule here that I'm just shading in red. So it's a benzene ring with 2 nitro groups and then this hydrazine, which is the NH2. The key point of this molecule is actually the NH2 group here, where I put the lone pair of electrons on the nitrogen. This NH2 group adds onto the carbonyl group of our aldehyde and ketone, so it kind of attacks this carbon here. The mechanism is quite complicated. We just need to know that it's an addition reaction followed by an elimination of water, so condensation. And what you end up with is this molecule here that I'll circle in green, and you kick out water. And this molecule here, its structure will depend on your choice of R groups. So whether it's a ketone, whether it's an aldehyde, depends what the aldehyde and what the ketone are. So these are R groups here. And this is insoluble. It doesn't dissolve in water, so you get a precipitate, which is a yellow-orange precipitate. So this is a good test for an aldehyde or a ketone. However, we can get more information than just the precipitate. 2,4-DNPH will confirm that it's an aldehyde or a ketone. However, if we take this precipitate and we filter it off and dry it in the oven, and then measure the melting point, and then look the melting point up in a table of data, you can work out which aldehyde or which ketone you started with based on the melting point. Now, you don't need to learn all the melting points, that's silly, but you need to be aware of the process that you take the precipitate, filter it off, dry it, measure the melting point, and then look it up in a table of data. And the result will tell you which aldehyde or ketone you had to start with. And then lastly, a test called the Haloform test or the Iodoform test, sometimes referred to as the triiodomethane test. And this is a test for methyl ketones, or molecules that can be oxidized to methyl ketones. So what do I mean by that? If you take propanone, hopefully you recognize that this is a ketone group, and it's a ketone group next to a CH3 group, which is a methyl group. So this is an example of a methyl ketone, and this will give a positive result. So I might just quickly add the definition to the slide here. Yep, so the Haloform test or the Iodoform test is a test for a methyl ketone or something that can be oxidized to a methyl ketone. So propanone is an example of a molecule that will give a positive test. If we compare this to pentanthreone, just as an example, I'm just picking a few examples to show you here. Pentanthreone. Now, pentanthreone has the ketone group on carbon number 3, and then there are 2 carbons either side like this. So it's a CH3 group here, then a CH2, then a CH2, and then a CH3. Now, this is a ketone group that is not next to a methyl group, because CH2 does not count as a methyl group. The CH3 is a methyl group. So this would not give a positive test because it's a ketone that isn't a methyl ketone. Just to show you an example of something that can be oxidized to a methyl ketone, if you take butantuol, so butantuol is a secondary alcohol, and you've got the alcohol group here next to a methyl group. Now, if you oxidize butantuol, you end up with butanone, and you end up with a ketone group next to a CH3 group, so this will give a positive test. And I've gone this far without actually telling you what the test is. The simplest set of reagents are you use sodium hydroxide and iodine. And the consequence is a yellow precipitate, which actually has an antiseptic smell as well. And the reason that you get this yellow precipitate is a bit complicated. I'm not going to go into the mechanism of how it happens, but basically your methyl group that's next to the ketone ends up being kicked out of the molecule in the form of CHI3. So basically the hydrogens on the methyl group substitute for iodine, and you end up kicking out CHI3, and it's this CHI3 that is your yellow precipitate. And this is why this reaction is sometimes called the triiodomethane reaction. Yeah, the triiodomethane reaction. And it's the CHI3 that is the yellow precipitate. And just to recap, it's the test for a methyl ketone or something that can be oxidized to a methyl ketone, like a secondary alcohol. Anyway, thank you for taking the time to watch the video. I hope it was helpful. If it was, remember to like, subscribe, keep checking back for more content, and I'll see you next time.